So thank you for coming. I kind of put the event at the wrong date, but the description had the right time. So I'm very happy that people showed up. So thank you so much. I see new faces. I think there's new faces. If you're new, can you raise your hand? Oh, there's a lot of new faces. Okay, so the way that these things work, it's like Elaine and I kick it off. She's sick today, so she can't come. So we wish her to get well soon and stop producing the things that she's producing that we don't want around. But normally what happens is that we have a very short meeting followed by a longer meeting, and not meeting, meetup, talk. And I tend to give you a little bit of information about the speaker, and I make something fake about them. So you have to guess which one it is. So our first talk is by Tony Arcieri. He's over there. And I will tell you a little bit about himself. So Tony is a Square engineering cybersecurity engineer. He cyber tweets about crypto and cyber privacy, not crypto. He's a Cyberinventor of celluloid and the cryptosphere. Tony was also a backup dancer for the Mickey Mouse Club till he got kicked out for excessive twirling. So let's give it up for Tony.
So I did just want to say the one true thing in there was that I was part of the Mickey Mouse Club. All right. So I am Tony Arcieri, and I am here tonight to tell you about macaroons, a better kind of cookie. So I work at Square on the cybersecurity team, where my day-to-day involves a lot of silhouetted figures in dark hoodies, neon-colored locks, binary and hexadecimal splattered all over everything. But the cool thing is we recently purchased keyboards with the cybersecurity key, and things have gotten a lot better since then. So I'm here tonight to talk to you about this paper, Macaroons, Cookies with Contextual Caveats for Decentralized Authorization in the Cloud. So what are macaroons? Well, they're like cookies, but they have layers. And why should you care? So I threw this slide in here somewhat facetiously, but in fact, I think there is a long-standing problem in security, which is rarely discussed, that macaroons actually solve. And this is something I guess I'll refer to as the 3+ principle problem. So perhaps you have a website, people log into it with some credentials, and they get back a cookie. It's probably familiar to most of you. Perhaps some of you have dealt with taking some sort of monolithic application and splitting it apart into a spectacular new service-oriented architecture. Now you have all sorts of various interesting interactions going on between all of your services. So what happens when there's an attacker? Or perhaps you're dealing with the Internet of Things, which in fact ends up looking quite a bit like that service-oriented architecture. So existing solutions to this general problem of distributed authorization are typically rather complex. So here is OAuth. Some of you might be familiar with that. I'm throwing all these graphs up here just because they look gross. You may have dealt with single sign-on. This is a system called CAS, Central Authorization System. This is the login workflow. And once you've gone through that, we get this nice simplified workflow, which still looks gross. All right. Or the federated access problem. This is SAML, or if you're familiar with it, something like JWT or CWT solves this problem. In fact, this is the simplified graph from previous systems where they used a even more complicated system. So what I would contend is if we can solve this problem, if we can solve authorization for at least 3 principles where one of them might be human and some of them may be services, we can solve any authorization problem. And yes, so the poo emoji, which I swear this is the last one in my slide deck, I'm using to indicate a principle, an entity, a participant, an authorization decision. So I'm going to give you a very brief and biased history of access control systems. Starting in the 1970s, there was a great battle between these 2 types of systems. So either authorization systems were identity-centric, so they focused on who you are, or they actually tried to express in a distributed manner actual authorization principles. So the main sort of school of thought around this was capabilities, specifically object capabilities. And if you know, one of the things I would like you to take away from this talk is you should go look into capabilities. They're super cool. There is a very rich history of papers around capabilities. It's kind of a unifying concept between concurrency, data as seen by a kernel or by an individual system, and data in a distributed context. So you should totally go check out capabilities. Unfortunately, these identity-centric systems won, and it's kind of like one of these things like functional programming versus everything else, where some of us may have a gut sense that functional programming is right in some degree, but unfortunately, we are still dealing with the mess that is the system that may be just like slightly more intuitive for people. So yeah, maybe they're right, and I think we should really reevaluate these concepts. So the main problem is ambient authority. So who thinks they know how set UID works? So if you do, you should look at this graph. So there are many types of ambient authority, even in Unix systems. So we have RUID, SUID, EUID, and this is a graph of a finite state machine that says how they relate to each other. So this is just completely incomprehensible. So for the most part, the authorization systems we depend on to keep everything secure just cannot be understood by humans. We get this sort of gross ad hoc logic that is just incomprehensible. So in the 1980s, we got this really cool paper. It was the Confused Deputy paper by this guy Norm Hardy. It wasn't really, your type of formal paper. It wasn't really an academic paper. It was just this guy writing a paper and telling it how it is. So I am going to give you a somewhat inaccurate retelling of how Trollface stole Christmas. So we've got our Confused Deputy. Here's Barney Fife. And we've got Trollface and Santa Claus. And so Trollface tells Barney to arrest Santa, and Barney's confused. He's like, why should I arrest Santa? So Trollface tells Barney I'm Andy Griffith, and that's totally cool, and now there's no Christmas. All right. So what happened here was we have Trollface with very little authority and Barney over here with a gun. And because of that, Barney got confused, arrests Santa Claus, and then we don't have Christmas. So what we really need is a system that respects authority end-to-end in these sort of multi-principle decisions. So that, we've got Cartman over here, and he has a little wee bit of authority, and Barney should just respect that. So another way of looking at this is when we have these sort of multi-principle decisions, we end up with someone in the middle that's trying to wear too many hats. So this service in the middle is trying to respect the authority of a user and also has all sorts of additional authority, and there are many users. So what we actually want is a system that is able to switch hats and respect the authority of the client and make all of these sort of multi-principal interactions use the sort of hat of the client that is making the original request. So back in bureaucracy land in the 80s, papers we don't love, we get this thing called X509, which is part of the ITU X series. So yeah, that's a big list, but the really crazy thing is the ITU had one of these for every single letter in the entire alphabet, and this is just X. So X500 or X509 comes out of this thing called X500, which was just the directory component of the X series, which was supposed to be this sort of all-encompassing global communication system, which these days we would just call the internet, right? So X500 is notable for practically nothing. Yeah, this is the Wikipedia, all the links are dead. There are only two things to take away from it. Was LDAP. LDAP is the lightweight equivalent to X500 and X509. So X509 would go into this thing called Netscape, and in particular, Netscape introduced security. It introduced HTTPS and a bunch of ciphers there. If you're familiar with them, they're all terrible, except for maybe RSA. But yeah, we got this X509 Pki. So this is, hopefully you're familiar with it, but it's sort of a centralized system where we have certificate authorities. We have clients who create certificate signing requests, give them the certificate authority, and we try to, in a central manner, give everybody certificates. And we get these fun certificate chains, which is how we verify that any given certificate is valid. And so, yeah, so this is a very complicated system with a lot of problems. And in fact, people were realizing this just in the mid-90s when this sort of thing launched. So can we do any better than this? So in 1996, some people were concerned and started working on an alternative. This is called Spooky and Sudsy. So these are effectively part of the same standard, but yeah, basically simple distributed security infrastructure. Here's the paper if you're curious, but it's a system based on S expressions that was trying to simplify the X509 Pki. So in the 2000s, there were a lot of cool papers. I'm just going to touch on one. This is probably the paper that makes my point for me the best. It's called Ackles Don't. Kind of came out of the capability school of thought. And here is the most important point. And this is, if you take anything away from this talk, I hope you take this point away. This is basically that every single system we build that does distributed authorization today is broken. So if you use Ackles or anything like that, they're not able to make correct decisions about authorization in a distributed context. They can't solve this 3+ principle problem. And yeah, we'll get to this guy soon. So macaroons. So here's the paper, a lot of Googlers' names on it, also name dropping Spooky and Sudsy, but the main two things are they're bearer credentials with caveats. So bearer credentials you're hopefully familiar with. A bearer credential in the traditional sense is anything you take around with you. It could be a driver's license, concert ticket, money, what have you. So the cool thing is these already have caveats. So these are a thing you're hopefully familiar with. We put these restrictions on a bearer credential, and these control how people interpret them. So they can be redundant. So we see 1, 1, 1, 1, 1 all over these things. The same seat at the concert, that kind of thing. They can be overlapping. Maybe not necessarily a good thing, but this actually does a fairly good job of illustrating how macaroons work. So we also have these contextual caveats. So you may be holding McLovin's driver's license here, but if your picture doesn't match, you can't use McLovin's driver's license as if it were your own. So macaroons are actually constructed. So let's take a look inside of a cookie. So we have this function. It's called hmac. Is a hash-based message authentication code. And what it does is we have a secret key and we have a message. And if we take the key and the message and we put them into hmac, we get back a uniformly random looking number as this tag that only the holder of the key is able to generate or guess and so forth. So here's an example of a cookie. We've got this user ID and maybe an expiration sort of caveat thing. We hmac it, we get this random number, and that acts as the tag that binds the message to the key. So macaroon, it's a little bit different, and here's where we get into the layers. So we start out with this identifier, which is sort of a key identifier, and this random nonce. So that's just a random number to uniquely identify this particular macaroon. And then we can add caveats to it. So here we're trying to add a expiration. CID just says this is a caveat ID. So these caveats are sort of arbitrary and domain specific, but this should give you the idea. So the way we add this caveat to this macaroon is we take the original tag and use that as an hmac key. And when we do, we get a brand new tag, and then when we're done, we can just burn off that original tag. And so what we've just done is added something that the holder of the original key can still identify as authentic, but once we've added it, it cannot be removed. At this point, we don't even need that original key anymore. We can continue adding these caveats in this sort of chain fashion. So we just repeat the same process, burn the original key, and we can continue adding caveats as the holder of a macaroon even without the original key. So this is very reminiscent of something called the Merkle-Damgard construction from cryptography. So it's not completely identical. So this is a slide from Dan Bonnet's crypto class, which I would strongly recommend you take if you're at all interested in cryptography. But it's sort of this construction that has formal proofs and we're fairly confident is secure. So I originally saw this, it blew my mind. But maybe you're wondering, so how does this actually help? So we can do some really cool things with this. So going back to that confused deputy, we can build systems based on authorization and not identity. So if we look at that cookie, we have this user ID, and what we would normally do with the cookie is take that user ID, look up in a database, try to apply some policy, pull in our domain objects, try to resolve this decision. And fortunately, not only does all of this require doing a bunch of database requests, but that nice policy scroll in practice probably ends up looking like a bunch of gunked up authorization logic, which is full of errors that the attackers want to exploit. So in a macaroon, what we do instead, so there's Barney Fife again. A macaroon, what we do instead of these, instead of using a database system, we use authorization caveats that explicitly spell out what people are allowed to do. So in this case, we have some domain-specific things. We got our widget, we have our operations we want to perform on them. So we have a subset of our widgets we're allowed to act on, and we have a subset of potential operations that we're allowed to perform. So when we do that, so we get a system that's based on what you can do, not who you are. But we can extend a macaroon with additional caveats that overlap the original ones, but form a sort of subset of what the original caveats were. So now we've limited this to a particular widget and a particular operation. So then we perform a set of checks to make sure all of the caveats hold, even though they're overlapping. And if they do, the authorization decision is allowed. And this process is called attenuation. So what this allows you to do with macaroons is this idea of delegation. So what you're probably familiar with is the sort of pattern on the left, where you have a client making a request to a service that makes a request to another service. The client has its original credentials, and then the intermediate service talks to this backend service with the full authority of all its credentials as that intermediate service. So this is how we get that confused deputy again, but go away, Barney Fife. All right. Another way we can do this is we can mint another credential, so this client is able to talk to this target service directly. So the intermediate service goes to the target service, goes, give me a credential exactly suited for this client, and then hands it back to the client, and then the client is able to talk to the target service. So what macaroons allow you to do is get rid of that network round trip, replace it with cryptography, and have this sort of intermediate service hand its credential over to the client, but attenuated so it can only access something specific. So this is great for things like if you want to share a URL to a specific photo or something like that, and you want to time limit it to 5 minutes or what have you, right? Practically any holder of a macaroon is able to do this, or any service which is authorizing things with macaroons is able to do this. So we can take the full authority of any principal in this interaction, attenuate it down to the specific thing we want to be able to share, and then create a new bearer credential, a new macaroon that you can give to anybody that expires quickly and gives them sort of like a brief amount of time to go interact with whatever thing they want to interact with. So in the title of the paper is contextual caveats. So contextual caveats, to go back to the McLovin photo, so we can put a caveat in that restricts a macaroon to a particular client. So this is an example based on token binding, specifically this idea of channel-bound cookies. So there's this new specification created mostly by Google to let your browser either automatically create a self-signed certificate for a particular site, or if you have a cool hardware token like a YubiKey or something, that can do the same thing. And you can actually bind any sort of cookie to either that certificate in your browser or to a hardware token. And you can encode this into a macaroon such that you need to be using that browser, using that hardware token to get to a particular thing. Another way to do this is the traditional X509 Pki. You can just give every principal a certificate and bind things that way. So I think this is a very powerful idea in that as soon as you take this macaroon out of that particular context, it loses its power. And this lets you do things like you can have a central macaroon service where you can, ahead of time, generate and publish macaroons, or have individual services generate and publish macaroons for the other services they want to interact with. And since they're contextually confined, they're not secrets. So you can just publicly publish this, everything can get to them, and you won't have a security problem. I think that's pretty powerful. So what makes macaroons truly unique? It's this idea of third-party caveats. So here's an example of this. I'm going to unconfuse the confused deputy. So we got Barney Fife again, got Trollface and Santa Claus, but now we have a sheriff. So Trollface still wants to arrest Santa, but this time Barney's going to say, you have to go ask the sheriff. Barney asks the sheriff, and no. Now Trollface is sad. All right, Christmas is saved, hooray. So adding a third-party caveat, this is pretty complicated. It's going to be a lot of keys flying around. I'm going to try to explain it as best as I can. But the basic idea is we can get rid of some of these round trips in something like OAuth using cryptography, and doing so adds some sort of privacy-preserving properties. So it works like adding any other type of caveat, but okay, so we're going to add this third-party caveat that's going to request this other service provide some sort of authorization. So what we're going to do is create a new random key, and we are going to take one copy and encrypt it under a key derived from the tag. And we're going to store that in the macaroon. And then we're going to take a third-party key. So this is some other service we want to involve in the authorization decision. This can be a symmetric key, it can be a public key, it doesn't really matter. So we're going to take another copy of that random key and combine it with that third-party key and also store that in the macaroon. So we have two keys at this point, one which can be read by the original service that holds the private key to this macaroon, and one that is the third-party service we want to authorize against. So now we have this other service that holds this other key, so we can take a copy of that and combine it with this other key. So this allows us to do something that macaroons model in the form of authorization logic. So now we want to so effectively this third-party service is going to create a second macaroon underneath this random key that was created by the original service. So we want to add a new expiration date that just says the service authorizes that decision until this timestamp expires. So we basically do the same thing where we HMAC it and create a tag. So now we have two macaroons, and we need both of them for the authorization decision to be considered valid. So this is called a discharge macaroon. So this is sort of using terminology from formal proofs. So this is effectively discharging the proof. So this is a holder of key proof. So all it's saying is this proves that the third-party service discharged that particular key. So it, at one point in time, knew that particular key. So that's all we need. So now to go one level deeper here, so we can nest third-party caveats. So any macaroon may have multiple third-party caveats, and discharge macaroons may also contain third-party caveats. So we can have sort of arbitrarily nested, arbitrarily structured graphs across any type of service you want to be involved in an authorization decision. So you can imagine you have a session service, you have a time-stamping service, you have a fraud service. It doesn't really matter, just whatever domain-specific services you have, you want to be involved in an authorization decision. You can express practically anything you want using this. And now for the really neat thing, if we flip this whole thing upside down, forms a proof of authority. So let's see, that can be formally proven to be rooted in that ultimate key. So this is the last page of the macaroons paper. So what they actually did was invented their own form of authorization logic, and the reason they had to do that gets back to that original point from Ackel's don't, which is existing authorization logic cannot solve this three plus principle problem. So typically authorization logic, which I mean this is a very simple logic, right? It's ultimately just modus ponens. But the sort of novel thing they added was the ability to model more than two principles. So effectively, existing authorization logic is broken because it cannot solve this 3+ principle problem. And this is perhaps the most interesting thing in the macaroons paper. So there are a number of open source libraries which implement the paper, and they're all interoperable, and there's a test suite which confirms they all interoperate and can all speak to each other. So hopefully you see the language you're looking for on this list. I'm the author of the Rust library, which is probably actually the one that is the least mature at this point. But if you're interested in using this, there is sort of an evolving open source ecosystem. And that's it. There's a link to the paper. There's this website, macaroons.io, which gives you some information about the format. If you're interested in talking about macaroons, I suggest you use the Google group. There's also Slack, although we don't really have a way to invite people. Should probably fix that. And otherwise, I am Bascule on Twitter. So, thank you.
Anybody has any questions? All right, that way. I'm starting with you first.
You've done such a good job of convincing me that capabilities are obviously better, and I do mean that.
Yeah.
I guess I wonder why they didn't win.
Why didn't they win? Because they're more complicated, and worse is better, and et cetera, et cetera. Probably at the time. So actually, I wanted to talk about more of this in my sort of like brief history, like 2000 section. Wasn't really until 2000 plus that I think capability ideas really developed into a nice, robust framework that we could actually use. And really, when the competition was happening was in the 70s. So I think they lost out because the ideas weren't developed enough. It was more complicated, and people just preferred things that were simpler. But now things are getting more complicated. There are more attackers. The attackers are more sophisticated. The attacks are more sophisticated. So, now is actually the time when we're actually starting to need this sort of thing. So capabilities are kind of making a comeback. If you've seen things like Capsicum in Linux and BSD, Google implemented Capsicum, so it's a capability-based API for doing POSIX-like things, for example.
So, yeah. I have a question about a scenario where, let's say, any stateless system, such as like a website.
Yeah.
Typically, you pass a cookie, you get the user, you check the ACLs like you said. Now, with macaroons, let's say my admin suddenly becomes rogue, like maybe the account got hijacked. In a typical scenario, just go to my database, change the ACLs, demote him from administrator to just regular user or something like that. And then every time I do that check, I go back to the source of truth, no problem. What happens? How do I invalidate that macaroon if I want to have the same effect in the scenario, since the client still has it?
Yeah. So this is exactly what third-party caveats are for. So you can mint a discharge the last 10 seconds or a minute or what have you, right? So macaroons allow you to do that sort of check. So you hold on to that discharge macaroon or potentially n discharge macaroons across n services that can sort of do that same sort of check, right? So if you have a session service, right, it's like, is my session still alive or is it expired, right? So the attacker, if they have a discharge macaroon, can continue to use it as long as it lasts, right? So what you want to do is make it very short-lived. So when that 10 seconds is up and you've invalidated their session in the database, they have to go get a new discharge macaroon, and they have to go back to that same service. So it's kind of like you have to go back to the sheriff, and now the sheriff's going to say no. So effectively, you have split credentials, and you have to periodically refresh them, and every single service that's part of that authorization decision must agree that is allowed. If any one of them says it isn't, then the decision is not allowed.
Any significant sites using macaroons in practice?
Yeah, so that's a good question. So I am still not sure what Google is actually using macaroons for. In terms of people I know who are actually using them, so there's a database called Hyperducts that base their entire authorization model around macaroons. And additionally, Canonical, if you're familiar with them, the makers of Ubuntu, built their single sign-on system with it. Beyond that, in terms of like who has actually bought into them, I don't have a whole lot of other examples. As to why that's the case, I think there's a lot more work that needs to be done sort of on the open source ecosystem around them. So there aren't good standards yet, there aren't well-defined test vectors, and the open source libraries that implement this paper are still relatively immature. So it's kind of an up-and-coming-ish evolving idea, I think. But my argument would be it is pretty much the only game in town that actually solves that multi-principal problem in an elegant way besides capabilities.
So I have a question around the size of macaroons. It sounds like a lot of caveats can be added to these macaroons, and recently there's been a lot of work in making time to first byte really, really short by sending as little data as possible. Do macaroons backpedal on this or hurt the time to first byte?
I don't really have a good response in that regard. So for I guess all I would say is if you look at sort of competing standards, like something like SAML, which uses XML, or things like Jose Web Tokens, Jose Web Tokens, that kind of thing. I think in general, macaroons have a relatively compact format compared to the other sort of competing-ish standards that they're competing against. So beyond that, I guess your question is probably around like, are these redundant checks bad or that kind of thing? I think in general there is a lot of focus on making them small and compact in ways that previous bearer token standards have done a really, really bad job with. So there's no XML, so that's great. There's not even any JSON. I mean, so there was a JSON version of the format, which, unlike JWT and CWT, is actually interoperable with the more compact format. But people abandoned, the makers of the libraries pretty much abandoned the JSON format and unanimously chose the compact format specifically for that reason, I think. So I guess the thing is, yes, there's going to be some redundancy, but I think if you're looking at the spectrum of alternatives to this problem, it's probably doing a better job than most of them.
All right. So let's give it up for Tony then. Yay. So now Gareth is going to be talking about the rendering equation, and I'm going to tell you a little bit more about him, because probably this is the first time you meet him. So Gareth has been involved in games and 3D graphics since 1999, started at Silicon Graphics, followed by several games companies, including Activision and BAM Studios. Since 2008, he has been working at Imagination Technologies, researching sophisticated rendering techniques using Imagination's ray tracing technology. Gareth recorded a hit single when he was 11 years old, and he cannot return to the West Berkshire without causing a paparazzi commotion. So let's give it up for Gareth.
Good evening. My name's Gareth Morgan, and I'll be presenting my Papers We Love talk on what I think is one of the most important 3D graphics papers of all time. That is James Kajia's 1986 SIGGRAPH paper, The Rendering Equation. So I'll give a little bit of background before I jump into the equation itself with another equation. The ultimate origin of James Kajia's rendering equation is Maxwell's equations. These were a set of equations formulated in the 1860s by James Clerk Maxwell. They are some of the most important equations in physics, alongside things like E equals mc squared and F equals ma. And they relate, they're a set of vector equations that relate magnetism to electricity. Because light itself is an electromagnetic wave, they also describe the behavior of light. So James Kajia took these equations and presented them in a form that could be approximated by a computer. So this is what he came up with, James Kajia's rendering equation. So what actually does this equation show? Why is it so important? If you look on the left-hand side of this equation, you see the term I. What is I? I, according to James Kajia, he described I as the measurement of the energy of radiation passing from some point in the world, x prime, to another point, x. Why is this important? Why does this matter? Well, if instead of saying x is some arbitrary point in the world, if instead we say x is your I, the rendering equation gives you an equation which tells you how much light energy will reach your eye at point x from any arbitrary point x prime in the world. This is basically the crux of 3D graphics as we know it. Anytime you see a computer-generated image, even going back to the earliest computer games like Doom, through to modern computer games like Call of Duty, as well as modern production graphics like DreamWorks Home, all the pixels of all these images are attempts by a computer to solve the rendering equation. So now I've hopefully explained and convinced you that it's an important equation. I'll go over some of these terms on the right here and try and explain to you what they mean. So the first term in the rendering equation is the geometry term. The most important aspect of the geometry term is it's zero if there's any opaque geometry between our 2 points. So if there's opaque geometry between our I at point x and the point we're trying to solve for, x prime, then the geometry term is zero. And as the geometry term is multiplied by the whole rest of the expression, if the geometry term is zero, the whole rest of the expression is zero. This makes sense from a common sense point of view. If there's an opaque object between your eye and a point, then no light will reach your eye directly from that point. The other aspect of the geometry term is an inverse squared law. If you've done any physics at all, you're probably familiar with inverse squared law for things like gravity or magnetism. And as I mentioned earlier, light itself is an electromagnetic wave, so the same kind of inverse squared law applies to light, that the energy transfer between our point x and our point x prime falls off with the square of the distance between our 2 points, x and x prime. The next term is the emittance term. This is pretty simple. If the surface that our point x prime is part of is itself a light, then most of the light that reaches our eye at point x from x prime will be photons that are emitted from that light, the surface of the light. That's very simple. It's simply the brightness of the light. The problem is, for almost all scenes, for most of the world, doesn't emit light directly. Most of the world, the emittance term is zero. But those bits of the world which don't have an emittance term aren't pitch black. So this is where the next term comes in, which is the integral. So for those other bits of the world which don't emit light by themselves, the light that reaches our eye from those points comes from all the other points in the entire world. So we have to integrate over all the points in the world. So within this integral, we now have a third point. We have our original point, our I point at x. We have the point we're trying to solve the rendering equation for, x prime. And we now have a third point, x prime prime, which is its other point in the world. And within the integral, we have two terms. The most important of them is this one, which is I again. So the rendering equation is recursive. To know how much light reaches our eye at point x from x prime, we need to know how much light reaches our eye at point x prime, reaches our point x prime from the third point x prime prime. Hopefully this diagram will explain it a little. So yeah, we have our point x at our eye. We have our point x prime we're trying to solve the rendering equation for. To solve that, seeing as x prime is not a light, we need to solve the rendering equation for all the other points in the world. And for each of those points, we need to solve the rendering equation again. So for each of those points, we also need to solve the rendering equation integral for all the other points in the world. So you can imagine that's quite a tricky equation to solve. The final point of our the final term in the rendering equation I'd like to talk about, and actually I'll talk about in some detail, is the scattering term. So we have our 3 points: x, our eye point; x prime, the point we're trying to solve for; and this third point, x prime prime. Only some of the light that arrives at x prime from x prime prime will ultimately reach our eye at our point x, at our eye point x. So the function that defines what percentage of that light energy arriving from x prime prime to x prime ultimately arrives at x, we use what's called a bidirectional reflectance distribution function, or a BRDF. This is a really important concept in computer graphics, so I'm going to go into it in some detail. The way a BRDF is usually defined is in terms of angles. So here we have our 3 points. On the right, we have x prime prime. We have the surface point we're trying to solve for, x prime, and our eye here on the left, x. We actually define the BRDF in terms of the angles relative to what's called the normal vector. If you've done any computer graphics at all, you've probably encountered the normal vector. This is a 3D vector that is exactly perpendicular to our surface at our surface point, so at x prime and x prime prime. Given that vector, we can now define our incoming and outgoing light direction using 2 angles. We have theta, which is the angle between the light vector and the normal, and we have phi, which is the orientation of the light direction around the normal. It's generally quite hard to describe for our brain to comprehend 4-dimensional functions. So for the purpose of this, I'm actually going to switch over to another application. This is the Brdf Explorer. It's actually a bit of software released by Disney Animation. And it's a way of visualizing these complicated BRDF functions. So here in this window at the top, we have our point, x prime, on our surface at the center of this yellow circle. And then we have, coming from our point, we have the dark blue normal vector pointing directly upwards. That's our normal vector. On the right, we have this light blue vector, which is the incoming light direction at our point, x prime. And you can see with this slider on the left here, I can vary the theta that defines this light direction. So if I bring the theta all the way down to 0 degrees, our light blue incoming light vector is directly parallel to our normal vector, but as I bring it out to 90 degrees, it becomes directly perpendicular. The other angle that defines that incoming light direction is phi. And that can go from 0 to 360 degrees, and as I vary it from 0 to 360 degrees, our light blue light vector moves around the normal. So that's how you define our incoming light direction. What about our outgoing light direction? Well, it's a 4-dimensional function, so we've defined 2 of the numbers that are parameters to our 4-dimensional function. How do we find the rest? Well, I can actually plot a BRDF function on this using this application, and that will show us the outgoing light direction. So this red hemisphere in the middle of the window is our BRDF. I've plotted the simplest BRDF of all, which is the Lambert BRDF, named after Johann Lambert, the 17th century Dutch physicist. And it simply says that regardless of our incoming light direction, our outgoing light direction is the same in all directions. So this is actually this plots the magnitude of the BRDF for a given outgoing direction as a shape in this window. And the shape is a hemisphere because the magnitude of the outgoing light is the same regardless of the outgoing light direction. So it just plots a hemisphere. A slightly more complicated BRDF is the Blin-Phong BRDF. So whereas the Lambert BRDF is a fairly good approximation of a very rough, diffuse surface, the Blin-Phong BRDF is a representative of a very shiny surface. And so it's basically zero almost all everywhere. So for a given incoming light direction, the outgoing light, the percentage of the light, the outgoing light is zero almost everywhere, except a really tight node centered around this pink vector here, which is our reflection vector, which is the vector we get when we reflect the light blue incoming light vector around the normal to produce this reflection vector. So for a small area of the sphere, of the unit sphere around that pink outgoing direction vector, we have a non-zero value for our BRDF. And that you can see by the green blob. The BRDF can have parameters which represent the surface properties at our point x prime. For the Blin-Phong BRDF has a power term that defines how smooth or shiny the surface is. So as the power term gets higher, sorry, I'm drawing the wrong BRDF. Sorry, that's why things weren't working right. So yes, this is the actual Blin-Phong BRDF. And as the power term gets higher, the node gets smaller. So only a smaller region of the outgoing light is non-zero. Almost all the light is reflected directly along the reflection vector. And if the surface was perfectly reflective, this function would be zero everywhere except exactly along that pink reflection vector. As the power term gets lower, the node gets bigger. And so this way you can vary the surface from a very shiny one to only slightly shiny one, to a slightly rougher surface. The final BRDF I'll talk about, very briefly, is the GGX BRDF. This is a BRDF that's actually commonly used in a lot of physically based shading systems that you've seen used in a lot of games recently. And the advantage of the GGX BRDF is that it can actually represent both a shiny surface and a very rough surface. So it has an alpha property, which when the alpha property is zero, we have a really, really shiny surface, really, really smooth. But as the alpha approaches 1, the BRDF approaches your basic Lambert BRDF. So in that way, you can define a bigger range of surfaces using just one BRDF. So that's a BRDF. As I mentioned, it's a really important concept in computer graphics, so I spent a while talking about it. Hopefully you now have some idea, possibly the best known 4D function you'll ever know, hopefully, maybe. Right there. Sorry, wrong button. Sorry about that, wrong button. Okay, so I've now explained what the various terms that make up the rendering equation. For the rest of this talk, I'm going to talk about how we go about solving it. As you might have guessed by all this talk of integrals, the way we solve the rendering equation is with calculus. I'm not a mathematician. When I used to read graphics papers, I generally skim through the calculus, and I find some code that I would understand. I actually think that's a mistake. For these kind of graphics papers, you really have to understand, most of it concerns calculus, so you really have to understand the calculus to understand the paper. So I'm going to take a somewhat first principles approach. Apologies if this turns this from a papers we love talk into a high school lessons we hated, or if it's extremely basic for you. So integration. Integration is represented by this funny S symbol here. And fundamentally, it's about solving the area problem. So we have our function f of x, which we can plot like this one here, is simply x squared. And the area problem is to tell us the area under our graph of f of x within a particular domain. In here, the domain is between 1 and 3 and the x-axis. So integration will tell us the area under the curve in this region here. What that means depends on what the function represents. If this function represented velocity, the integral of this function would be the distance traveled between 1 second and 3 seconds. If this function represented the change in share price, it would represent the amount of money we've earned between 1 day and 3 days. It's a pretty fundamental mathematical process. I'm sure when you were taught integration, you were taught analytical integration. In analytical integration, we symbolically manipulate our function f of x to produce the integral. So for a simple polynomial like this, we take x squared, we add 1 to the power to produce x cubed, and divide by the result. So we get 1/3. The integral of x squared is 1/3 x cubed. We then we feed that into the minimum maximum of our domain to produce a result. So the integral of x squared between 1 and 3, the area under the graph you see here is 8 and 2/3. Really basic stuff. Why am I even talking about this? Well, what if the function we're trying to integrate is more complicated? What if it's the function itself doesn't lend itself to symbolic integration, analytical integration? Or what if the function itself is some complicated multi-dimensional function like this on the right? You rapidly get into the point where it's very hard to integrate our function using analytical integration. For these kind of functions, you can use what's called numerical integration, specifically Monte Carlo integration. And this is the way James Kajia suggested solving the rendering equation. Brief historical aside here, numerical integration was actually invented by this guy, Stan Ulam, along with John von Neumann, Enrico Fermi, and Nicholas Metropolis, who at the time were working on the Manhattan Project during World War II to create the first atomic bomb. And they worked out to solve these kind of really complicated integrals that couldn't be solved with analytic integration. You could use the power of statistics. Particularly, you could use the power of electronic computers. The reason Monte Carlo integration didn't really take off until the 20th century is, even though the concept existed before the 20th century, it took the power of computers to really make it feasible. In particular, during the Manhattan Project, there was the Eniac computer, although the thing Stan Ulam is holding in his hand there is actually a mechanical computer. So the Eniac wasn't actually available when they first came up with the concept of Monte Carlo integration. It was busy computing artillery tables. So they came up with this mechanical computer for doing their Monte Carlo integration. The problem they were trying to solve was the problem of neutron scattering in the core of the atomic bomb. And actually, the solution they came up with this mechanical computer, very similar to the way James Kajia ultimately solved the rendering equation. Random historical aside there. So how does Monte Carlo integration work? So basically, it's using the power of statistics and probability to come up with an approximation of your integral. So you choose a uniformly distributed random number within your domain. So our domain here is between 1 and 3. We choose a random number, or as we're using a computer typically, a pseudo-random number, a difference I'm not going to get into right now, somewhere between 1 and 3. We evaluate the function at that point, and then we compute another point, and add them together, and compute an average. And then we multiply by the size of our domain. And then we keep doing this. And I don't know if you can actually see the lines on this graph, but as we compute more and more points, the value that we come up with this way gradually approaches the actual correct value of our function. To get an exact value, the exact value of our integral, we need an infinite number of points. But the point of Monte Carlo is you don't actually need an exact value most of the time. You can come up with a pretty good approximation with actually a small number of these samples. The problem with numerical integration is the problem of convergence. What I've done here is I've plotted the error, the difference between our approximation and the correct result over time. And the problem is you need a lot of, to get a good approximation using uniformly distributed numbers, you need a lot of numbers. And particularly for the problem of the rendering equation, we're trying to solve it for every pixel on the screen. So we need to solve a lot of integrals. So even with a powerful computer, if we If we just use uniformly distributed random numbers and try to solve it with brute force approach, we'll be there a long time. The reason for this is basically goes down to a basic property of random numbers. Here I've plotted a few random samples, and these are genuinely uniformly distributed random samples, but you may notice they don't really look very random. They look kind of clustered around certain points. And it's not a problem with my code. These are actually uniformly distributed pseudo-random numbers. But the fact is, when human beings look at random numbers, they don't look random. They tend to form these clusters. This is one of the reasons for the gambler's fallacy. So if these were numbers on a roulette wheel, you'll be thinking, oh, we want to bet on 2.2 or 2.6. But actually, no, you shouldn't. 2.2 is exactly as likely as 1.6 or 1.8 on this weird roulette wheel. It's just you tend to get these clustering of uniformly distributed random numbers. That's the way they work. And for Monte Carlo integration, this is a problem. We've basically oversampled our function around these points where the samples are clustered, and we've undersampled it in the points where you don't have many samples. So a huge part of James Gagia's paper is actually talking about solving this problem. I don't actually have time during this talk to talk about how he solved it. But basically using things like stratified sampling, importance sampling, hierarchical sampling, and adaptive sampling, you can get much better convergence than you will with just purely uniformly distributed random numbers. That said, I don't have time to talk about this now, so just for the rest of this talk, when I talk about random numbers, just assume you don't really want to use random numbers for these kind of rendering equations. You want to use another type of number. Okay. So now we can solve really simple one-dimensional integrals. Great. You may notice the rendering equation is not a really simple one-dimensional integral. It's this very complicated, multi-dimensional recursive function. So how do we solve that using Monte Carlo integration? Well, the first thing to note is that, actually the rendering equation is a Fredholm equation of the second kind. What does that mean? I don't actually know. I'm not a mathematician. I have no idea who Fredholm is. Probably a long-dead 19th century European mathematician who's never been referenced in a Pixar movie. But the key point about a Fredholm integral equation of the second kind is it can be simplified using a Newman series. That is an infinite numerical series. The first term of our series is simply our first geometry term multiplied by our first emission term. The second term of our series is our first geometry term multiplied by our first integral. And inside that integral, there is exactly one emittance term, which is our second emittance term. That is the key point about the Newman series. Every term in the Newman series has only one emittance term. So here we have the integral of all our x prime points that are light emitters, and the light that arrives on them at x prime. The third term is that integral with another integral inside it, and inside that integral is our third emittance term. This is getting kind of confusing. The way this was simplified by James Gagia is using linear operators. So, the first thing he did is just all the geometry terms and emittance terms just become g's and epsilons. Then all the integrals he represented using the linear operator m. So they simply become m. The advantage of linear operators, I hear, is that you can actually use a power term with a linear operator. So subsequent terms of the equation just become m cubed and then up to m to the n. So we now have a very simple-looking symbolic representation of our rendering equation as a numerical series. How does it help us solve the rendering equation? Well, it turns out all these terms have actual real-world interpretations that actually mean something. The first term is the light that arrives directly at our eye if our point x prime is a light. There's no integral important term, that's just it. It's just a constant value. The next term is the integral of all the points that are themselves, is the integral of all the lit points that bounce, all the light that leaves the eye, bounces off our point at x prime, and then arrives at our light at our point x. The next term is all the light that leaves our light, hits the surface, bounces off, hits another surface, then arrives at our point x prime and bounces off and reaches our light. So each term in the rendering equation represents a bounce of light. This is actually the key to solving the rendering equation. So the first way James Gajia suggested solving it is the way it has actually already been solved. He called it the Utah approximation. That is named for the University of Utah, where a lot of the really key fundamental work, early work was done in computer graphics. And so one thing to note about the rendering equation of this form is each term, there is less energy in each subsequent term than there is in the last. And each time the light bounces, we run our Brdf, and only a small percentage of that light ultimately arrives at our eye from that point. So each term gets smaller and smaller. So the Utah approximation just says, well, we can just ignore everything after the first two terms. So really all we care about is the light that arrived at our eye directly from the surface, and the light that bounces once and then arrived at our eye. This is a way almost all computer graphics had been done before James Gajia presented the rendering equation, and it's actually the way most real-time computer graphics are done to this day. If you've ever written a program in OpenGL or DirectX, and you've written a light loop in your shader, and maybe taking in that's your integral. That's your integral M here. Running over all the lights in your light loop is the integral. If you've run a shadow map on each of those lights, if you've executed a shadow map on each of those lights, that's actually your second geometry term. And then your light color is just that emittance term. Basically, this was the way, basically the way graphics were done, particularly in real time, for many, many years. But even though most of the light comes from this, most of the light energy arriving in our eye comes from these first two terms, your brain knows the difference. If you exclude those other terms, even though your brain will notice that it doesn't look quite right. So this image here is an example of that. It's a good real-time rendering of a simple scene, but it doesn't look quite right. So what if we want to actually include the contribution of those other terms? I have lost a slide. Sorry. That was like the crux of the whole presentation. So, the answer is ray tracing. The secret of comedy is timing. Ray tracing wasn't invented by James Gajia. It was actually developed by Turner Whitted in his really important 1980 paper. It's basically quite a simple concept. You basically store your world in a database. So you store all typically the triangles that make up your world in a database in world space, along with the surface properties. So all the properties you need, all the colors and constant terms you need to evaluate your Brdf at every point on your surface. You store that in the database, and then you query it, just like any database. But the way you query a database in ray tracing is you use array. Array is an infinitely thin geometric primitive. It has an origin in world space, a direction vector in world space, and a length. So you feed that array into your database, and it gives you a result. The result is the nearest point along that array to the origin, along with the surface properties at that point. The way Turner Whitted used this is to produce this kind of image here. It's taken from Turner Whitted's paper. So you shoot a ray from your eye point for every pixel in the scene. You see what that ray intersects with. You evaluate its surface properties, and then you emit more. You emit another ray. So, for example, to simulate the refractive sphere, or the refractive sphere, or the checkerboard floor, or you shoot a ray at the light to do the shadow. This is the way Turner Whitted used ray tracing. What James Gajia worked out is that actually, just like in our 2D Monte Carlo integration case, each ray, if you choose a ray with an origin at x prime and choose a random direction to shoot that ray in, that's just like computing your random point in the domain in the simple 1D case. That is, you're sampling the integral that makes up the rendering equation. If you shoot your random point and it hits a light, you've computed a sample in your first integral. You calculate your light color, the intensity of the light. You compute your Brdf at the point x prime, given your I point at x, and that's your sample point. If you shoot your random ray and it hits another point in the scene, that's your point x prime prime, and you need to shoot another ray from there. This time we use our point x prime prime as the ray origin. We choose a random direction, send it on that point, shoot it out into the scene. If that ray hits a light, you now have a sample in the second integral, the second term of our rendering equation, or the second integral in our rendering equation, and so on. If that ray happens to hit another point that's not a light. At each point, whenever we hit a light, we have our sample. We compute all the BRDFs up to that point, and that gives us the final value we've sampled, just exactly the same way as when we chose our point in our 1D example between 1 and 3 and evaluated our function. That's exactly what we're doing here using ray tracing. So this method of ray tracing can be called path tracing. It's quite simple. So you shoot just like in Turner-Whitted's ray tracing. You shoot a ray for every pixel that hits a point, our x prime point. You shoot another ray from there, randomly selected in a random direction, and eventually the light, that ray will hit a light. At that point, you've computed a sample. So you go back to the beginning and start again. You shoot another ray. You shoot another ray. Maybe this ray hits one point, then another point, and then hits a light. So you've now sampled the second integral in our rendering equation, and so on, and so on. At some point, you actually want to just give up. Rather, if your part hasn't found a light, again, every subsequent term in the rendering equation is less significant to the last. So at some point, you say, well, rather than bouncing around forever, even if we were to find a light at this point, the contribution will be so small that it's not worth it, so we just give up. So gradually, as you shoot more and more paths through the scene, you compute more and more samples for every pixel in the image, and your result will converge on a photorealistic, accurate approximation of the rendering equation. That's path tracing. That remains the gold standard of photorealistic graphics. To make this point here, so here's on the left here is a picture I found in a path tracing paper of the Sponza atrium scene. It's one of the most famous scenes you'll see in computer graphics papers, along with the Cornell box and the Utah teapot that I've been using up to now. And you see on the left a pretty good, very, very accurate photorealistic solution for the rendering equation for that scene. And actually on the right here is a photo of me in the actual Sponza atrium. It's a building in Croatia, in Dubrovnik, Croatia. Just to prove the point that it is a gold standard. Whenever you see an image that's been produced for like a Hollywood movie or a kind of ground truth image from a graphics paper where someone that's coming up with a rendering technique is comparing their technique to a ground truth, probably that image has been generated using path tracing. But that is not the only way to solve the rendering equation. The fact remains, whenever you see a computer-generated image that attempts to mimic reality, you're seeing a solution for the rendering equation. And nowadays, in computer graphics, you're seeing a bunch of really accurate, really fast ways of approximating the rendering equation that don't necessarily use path tracing, but can be executed in real time. And so more and more nowadays, you see people actually take it seriously in real-time games as well as in production graphics. So I've really had to skim over a lot here. I barely touched on a lot of subjects and had to cut out a lot. So if you want to know more about it, I recommend reading Physically Based Rendering from Theory to Implementation by Matt Farr and Greg Humphreys. It is the definitive tome on the matter on photorealistic rendering. It actually won an Oscar, interestingly, this book. I'm not kidding. So finally, if you enjoy talking about this kind of thing, I do have a meetup group, Nerds with a U, on meetup.com. And I also have a book if you'd like to buy it. It's not won an Oscar yet, but I do have a chapter in the latest edition of GPU Pro 6 entitled Hybrid Ray Tracing on a Power VR GPU, out now on CRC Press. Thank you. Are there any questions?
Hello. Yes. So how does the tools, like the tool chats, like the tool chains, like look like? Because I mean, are you supposed to keep the things in your head as you're like a graphics engineer?
No. Nowadays there's very mature tools. Like back in 1986, the tools were pretty primitive. Nowadays, depending on your application, like production graphics has a really mature set of tools and renderers, and real-time graphics has a lot of game engines and people that have done this for you. So when you're using Unity or Unreal or 3ds Max with a particular renderer, you don't have to know what the rendering equation. You just need to know how to use the tool. So there are now actually very mature tools.
So you think that it's a good thing or a bad thing?
I actually think it's a good thing. I think it's I think really? I have obviously I'm biased because I work for a ray tracing company, but.
Right. Coming to you.
Hi, I was wondering, are there extensions that have been made to the rendering equation to deal with things like polarization or fluorescence or like color shifting and things like that?
Yes, to have actually somebody else. This is the last talk, the mini talk I did. Yes, so I actually glossed over the whole matter of color. So the way it's generally handled is, all the values you see in these equations are actually they're not just one value, they're three. You just have a red, a green, and a blue value. And then technically, every BRDF actually is three BRDFs, one for each, the red, green, and blue. Although generally the way it works is basically the BRDF just has a color value or multiple color values, and your incoming, the result of your BRDF is scaled, or some component of it is scaled. But actually, some BRDFs do handle that kind of thing, where it's like actually each color component has a separate BRDF that handles that kind of thing. And then really sophisticated ray tracers that are actually trying to simulate it, almost more, in a more sophisticated way. They will actually deal with polarity and wavelengths and things like that.
Any questions? Fine. It's just for the video.
So in a practical ray tracing algorithm, is it important for the image generation to be deterministic? So like is the selection of the rays actually heuristic rather than random?
Of course, it's not actually random. It's pseudo-random is the way, if you're doing it in software, all software is deterministic. And so that's the difference between a pseudo-random number and a random number. If you have this in hardware, for example, the imagination's hardware, you do get sometimes the hardware can be non-deterministic, but it's still, there's ways of solving that problem to make it deterministic. More importantly is the way you choose the samples in your domain than the actual determinism. Is that I say uniform. You rapidly, even in fairly trivial examples, you rapidly get really bad convergence if you're just choosing uniform. That's like the Fisher-Price my first ray tracer will use uniform sampling, and you rapidly want to use actually not random numbers at all. Like you want to use you either use stratified sampling, which are random numbers, or other types of sampling which aren't actually random.
Okay, you're on the way.
The occlusion factor, you call it geometry factor in Maxwell's equation, seems to put 100% block on the light as if it were photons, particles. If you're dealing with, if they've also extensions to deal with polarization, which is waveform, do they also deal with some of the bending properties where light actually shines around corners in the waveform?
So refraction is very much, So basically, refraction definitely is that. So the BRDF, you generally think about a BRDF as just the hemisphere. But actually, if an object's transparent, the BRDF is actually 360 degrees, not just 180 degrees of the full sphere there. And so yes, the Brdf is actually a 360-degree function that represents some of that light is going through the surface as well as being reflected off.
Could you just expand a little bit? You said that there's extensions to the equation for polarization, but the question is that since it seemed like the equation was just a restatement of Maxwell's equations, I thought Maxwell's equations were already, you know.
I've never done ray tracing that involves polarization, so I couldn't actually answer that. Yes, I believe that there's ray tracing the way that's used for 3D graphics. So even production 3D graphics, while it does have some more complicated light effects, doesn't really. But then there's ray tracing for physicists who are actually trying to simulate like real light transport. That they don't just need a pretty picture; they're actually trying to work out exactly how photons transport, and they do have to deal with that. I've never even seen that kind of thing in action, but I know it exists. It is, and they do use ray tracing for it. But I don't actually know how they handle that.
I have a crazy friend who a long time ago created a modeler which emitted photons from all the light sources in a random way and had a pinhole camera. And if the photon magically managed to go through the pinhole, then you got a hit. Mm-hmm. And the reason I know about it is he stole every computer we could find and ran it for a long time. And eventually this very fuzzy image gradually became slightly more, you could actually start to gradually see what the thing, it was very, very, very high fidelity, took forever. So that's why you don't do it that way, I guess. Mm-hmm.
And there are a bunch of ways to do it the other way. Like there's various ways you do. Like this is reverse ray tracing, is where you start at the eye and work outwards. There are like innumerable techniques. Since 1986, there are 1,000,001 different variants on this techniques, and and many of them are actually based on emitting rays from the light and from the eye, and various different combinations of that.
This may be a naive question. Is there still competitive advantage in gaining efficiencies in computing the rendering equation and ray tracing and all that, or are we at the point where we have enough computational power that your code can be naive and it'll still be fine?
Well, the key point is that actually you're rapidly, you'll actually run out of bandwidth sooner than you'll run out of compute power. Like you have really powerful GPUs out there, really powerful, particularly GPUs. But if you do just take a brute force approach, long before you'll be starving the GPU and so the compute will just be idle. But it rapidly just becomes a bandwidth problem very, very, very quickly. Just because you're basically doing, as you can see by some of these slides, you're basically doing random, basically that looks like random access in a lot of ways.
Stretching.
There's sort of an anecdote to answer, to respond to that question. And I don't know exactly how true this is, but apparently every Pixar film, it takes an hour to render each frame because even though the computers are getting faster, they're just going to make more complicated scenes. And the threshold that they've sort of settled on is when it takes about an hour to render a frame, that's as far as we're going to go. So do they want them to be more efficient? Yes, they do want the techniques to be more efficient as much as they'd like the computers to be faster. So anyway.
Yeah, you gave 3 examples of BRDFs that kind of make the image look pretty and how we want it to look like, but how do you measure an accurate BRDF, or is that such a thing?
It is actually. Interestingly enough, the Cornell box you see here, it is actually a physical thing. So when they first did these, this is actually another approach to, actually predates Kaguya slightly, which uses finite element analysis. And they built this box and took pictures of it and worked out how to do the math in such a way that it looked like the picture they took. So there's a lot of complicated math involved, but it is very much like a BRDF is a physics. It's not just a computer graphics term. It's an actual thing.
Hi, I'm curious about the limits of this model for understanding things. So diffraction effects. All these diagrams show sort of reflected rays.
Yep.
I was wondering, can you also configure the BRDF so that it's modeling diffraction effects in the same way that you're saying you could do it for refraction with transparent surfaces?
Yeah, so in, not in the original paper, but yeah, since then it has been, yeah, so you mean actually like, where the actual medium itself isn't just air, it's something that has stuff in it?
Light hitting edges or small cracks, passing through areas where the wavelength of light is relevant.
Yeah, you just have to make, there's been extensions to it that have done that.
Another, we're thinking about extensions of it. Like if you think about the sort of imaging that submarines would want to do with sonar, where you're using some wave-like medium that's not light, or if you wanted to like model spaceships zooming around where there's like gravity and relativistic effects. A lot of that. I mean, how much of this model is general, and how much of it is really limited to situations where you can usefully think of light as always going sort of straight and bouncing off things?
So I mean, the big thing actually, so one of the big additions to this model since James Garcia produced it was that the idea that actually the thing the light is traveling through isn't just air. There's fog in the air or smoke in the air or water. That kind of transmissive medium. So that will totally and actually modern production renderers and not real-time renderers too do take that into account. In terms of relativistic effects, the people who are doing it for simulating, galaxies spinning around, they totally have to take that into account. Most production renderers did, although I did see there was a paper on for Interstellar. Apparently, they did actually change their path tracer to take into account relativistic effects. I don't know. I don't actually know. I didn't actually read the paper, but it might have just been PR. But for doing the black hole in Interstellar.
So in a way, for me, this has been like introduction to 3D graphics. It's like, did I miss something? Is there any sort of like account for the type of texture that I'm dealing with? Because you're talking about like how light bounces off, but I mean, does it matter whenever you have something that is like porous versus something that is supposed to be glossy versus something that is supposed to be?
So that's basically the BRDF. That is basically the essence of the BRDF is to represent like what surface is this? How does it reflect light off? Like, is it transparent? Is it glossy? Is it matte? And that is, that's basically what the BRDF represents.
Because I heard you said that, but it's almost like, I mean, so basically you can just represent glass versus like hair in that way?
That's basically the BRDF in its fundamental form is like, the difference between glass and hair and wool and metal, that's the BRDF.
Do we have any feeling in the real world for what are the major components of the BRDF in real surfaces?
There's quite a bit. There's like it's a fairly well understood. Not being a mathematician, generally as someone who just consumes this kind of research rather than actually like does it. I think it's a pretty well understood. So basically, the main model used nowadays is the microfacet model. That basically it also boils down to basically a statistical thing. That basically you consider it if you look at your surface. It's a bunch of like basically you consider each like minute facet of your surface is a perfect mirror, but you have like a whole bunch of them like on a microscopic scale, and so actually the BRDF represents the orientation of those like tiny facets statistically. Is basically that's the microfacet model, which is like I think most BRDFs are based on.
Any questions? All right, let's give it up for Gareth.